I wanted to look at a example or show you an example involving power and power dissipated. So in this particular problem, it says calculate the power dissipated by air resistance for a coffee filter that's falling in free fall. And so before I go on to calculate the power dissipated by air resistance of the coffee filter falling in free fall, I just wanted to show you the situation. You can see this situation at home in your kitchen. I can show you this situation here at work in my office. And we're just going to look at free fall of the coffee filter and then just talk a little bit about free fall of the coffee filter. So I've got a coffee filter here. And I'm just going to drop this coffee filter to the ground. Now, easy experiment, simple experiment, but if you think about the experiment, it's kind of interesting. The coffee filter, you might have noticed, did not accelerate towards the ground with the acceleration of gravity getting faster and faster and faster. Rather, the coffee filter kind of glided towards the ground without accelerating, going at constant velocity. And that's the situation we call free fall. If you jump out of a plane with a parachute, you'll be in free fall as you fall through the air towards the earth. And that coffee filter that jumped out my hand was in free fall as it fell towards the floor. And what's happening in free fall is that there are two forces that are acting on the coffee filter. So there is the force of gravity that's of course pulling the coffee filter down towards the earth. But there's the drag force of the air's resistance that's opposing the motion of the coffee filter towards the earth. And in free fall, if you're a parachutist in free fall, if you're a coffee filter in free fall, what's happening in free fall is that the gravitational force downwards is balanced by the air resistance, drag force upwards. And so the net force on the coffee filter or the parachuter is zero. And so the coffee filter moves with constant velocity towards the floor. The parachuter moves with constant velocity towards the ground because of this balance of gravitational and drag forces. Now, from the perspective of energy, the gravitational force is doing positive work on the coffee filter or the parachutist because the gravitational force is in the same direction as the motion of the coffee filter or the parachutist. On the other hand, the drag force, that's doing negative work on the coffee filter or the parachutist because it's opposite the direction of motion. And so from an energy perspective or a work perspective, the gravitational force is doing positive work on the parachuter or the coffee filter, and the drag force is doing negative work on the coffee filter or the parachuter. And we're going to figure out the rate at which that work is done, the rate at which work is done on the coffee filter by the drag force. And that would actually be equal and opposite to the rate at which work is done on the coffee filter by the gravitational force. And that rate at which work is done is this quantity we call power. It's this quantity that's measured in joules per second. It's how many watts of energy you transfer per unit of time per second. And so let's go ahead and calculate that. Of course, I'm going to start with a sketch. So here is my coffee filter. It is falling towards the ground. Here's its motion. And we know, or we're told, a couple of things about the coffee filter. Well, its mass is 1.8 grams, or 0.0018 kilograms. And its velocity, we're told, is 1 meter per second. That's the terminal velocity. And actually, you saw that in the demonstration. You saw the coffee filter fall about a meter, and you saw that it took about a second. So that's a meter per second. So we actually measured that. Okay, so that's the information we're given. Now, we've explained that the situation for this free fall is that there is a gravitational force downwards and a drag force upwards, and they're equal and opposite. So let me just picture those. Here's gravity acting downwards, and here's the drag force acting upwards. And the gravitational force, which is mass times acceleration of gravity, is going to be 0.018 newtons. And the drag force, I'm going to call it F subscript D for drag, that's equal in size to the gravitational force because we're in free fall. And so that is also 0.018 newtons. So that's a picture of the situation. Okay, so now we want to calculate the power dissipated by the drag force. And in class, we met a couple of equations for power. We met the relationship between power and work. That was one equation. And the other equation we met is the relationship between power and force. So this would tell us the power dissipated, for example, by the gravitational force, or by the drag force, or the power supplied by the gravitational force. So that equation is that the power, and it could be power supplied or it could be power dissipated. In this calculation, it's going to be power dissipated rather than supplied, is equal to the force multiplied by the velocity multiplied by the cosine of the angle between the motion, the velocity vector, and the force vector. And so I've written this for our particular example of the drag force. So this is the magnitude of the drag force. The terminal velocity, this is the terminal velocity of the coffee filter. And this cosine 180 degrees is because the motion is downwards, the drag force is upwards. They're in opposite directions. So all we have to do is to substitute in the numbers, the drag force, tiny little force for a small coffee filter, 0.018 newtons, the velocity, 1 meter per second, and the cosine of 180 degrees, you remember this, I remember this, -1. And so if we multiply all those things together, we get the drag force. If we multiply all those things together, we're going to get the power dissipated. It's going to be negative 0.08, and it's watts, which is a joule per second. And so that's the power dissipated by the drag force. It would also be the 0.018 watts would be the power that's being supplied by the gravitational force. And so that's a simple example of power. And so, I mean, one of the reasons for doing this example is again to show you that there's different ways of looking at situations. We could look at the situation of free fall from the perspective of the forces, and we actually did that to begin with. We analyzed the gravitational force and the drag force. You can also look at it from the perspective of energy and energy transfer and rate of energy transfer. And we've done that as we've looked at this problem from the perspective of work being done by gravity and drag forces and the power being dissipated or supplied by gravity and drag forces.